Hello everyone, welcome to the NPTEL online certification course on fundamentals of food process engineering. So, we will continue with food rheology today. In the last class we have seen the material property of solid, and we have also learned the three different modulus, that is Young's modulus, bulk modulus and shear modulus, and also we have familiar with certain parameter of the rheological nature of the solids, and stress tensor also we have discussed a bit. And today we will move further to a very important concept, that is called the Poisson's ratio. Now, when we have discussed about the unidirectional or uniaxial force, that time we have noticed that when we are pulling the body from the both end in a unidirectional manner, so the elongation has happened in the body. Okay. That means, in the direction of the force the body has been elongated, some deformation or some length enhanced in that direction, right. Now, since the body volume cannot be changed, because we are not exposing it to the bulk compression, right. So, in this case, if suppose some changes happen in the longitudinal direction, so definitely some amount of change will also need to happen in the transverse direction, because the volume should remain constant, right. So, Poisson's ratio deals with this concept, that is, because the volume of the sample cannot change under simple axial loading. If a unidirectional tensile stress increases the dimension in one direction, the dimension in the transverse direction must decrease, okay, and the relative change in the thickness, that is delta d by d, is called the transverse strain, and the it depends on the axial strain, that is delta L by L. So, the ratio of the transverse strain to the axial strain produces a proportionality factor, that is called the Poisson's ratio mu. Okay. So, Poisson's ratio mu, that is equal to transverse strain by axial strain, and this is very important parameter. If we know the Poisson's ratio and we know that any other parameter between all the three modulus, that is E, K and G, capital E, capital K and capital G, we can find out the other parameters. So, the interrelation can be visible from this table, that we have taken two material, case A and case B. So, in case A, what we are getting, that mu is equal to 0.5 and case B mu equal to 0. That means, mu is the Poisson's ratio. So, Poisson's ratio is transverse direction, relative change in the transverse direction or transverse strain divided by the longitudinal strain. Okay. So, delta d by d divided by delta L by L. So, this value is equal to 0.5. That means, the transverse strain, that is equal to half of the longitudinal strain in the first case, whereas in the second case the longitudinal strain is so high that mu value is coming 0. Okay. So, in this case, if mu is 0, 0.5 and mu is 0 in case of A and B, we know that there are different interrelation like shear modulus G, bulk modulus K and Young's modulus E, that can be expressed in terms of these other modulus. So, if we try to find out G or shear modulus, E divided by 2 into 1 plus mu, where mu is equal to 0.5. So, G we are getting E by 3, that is 1/3 of the Young's modulus will be the value of shear modulus. Okay. Similarly, K, that is the bulk modulus. So, that is coming infinity. Okay. So, bulk modulus is coming infinity. Now, what is the bulk modulus? That is the relative change of pressure needed to cause the relative change in the volume. That means, the pressure, the requirement of the pressure will be so high to cause the change in the volume in this kind of a sample. And here, because we have got this one in G equal to E by 3. So, similarly, E will be 3 times of the shear modulus. In case of B, however, we are getting G equal to E by 2 or 3 by 2 into bulk modulus. Here the bulk modulus is equal to E by 3. So, in the first case we are getting shear modulus as E by 3, in the second case we are getting the bulk modulus as E by 3, and further we can get the expression of K in terms of Poisson's ratio only, that is Poisson's ratio in an shear modulus. So, all the interrelation can be generated. So, if we try to find all the values of this kind of two material. So, for material A we are getting K is very large, that we are getting from here. So, the bulk modulus will be very large, E is small, okay. Young's modulus is small. That means, if you plot this stress versus strain in this particular matter, so we are getting a very low slope, okay. So, that means the change of the change to cause a certain amount of strain, small amount of stress is required, okay. Similarly, G is also we are getting small, but for material B where the bulk modulus is small. So, E we are getting very large and G also we are getting very large value. Okay. So, K, G and E all we can relate with the other property or in terms of the Poisson's ratio. Okay. So, this is the expressions. Now, we will move on to the next thing, that is the fluid behavior or viscous property. So, till now we have mostly concentrated on the solid behavior, rheological behavior of the solid, that what happen when the solid material is exposed to normal or shear stresses. Okay. Also the concept of tensor, stress tensor is very much applicable to the fluid. So, now we will going to see in a bit detail that what are the fluid behavior or viscous properties. So, fluid behavior in a steady shear flow. So, the way in which liquid deform to an applied stress is flow, that is the continuous deformation with time. So, let us take a fluid which is kept in between two thin plates and the gap between two plates are very less. So, H is very less, okay. And from the rest position, if the bottom plate is fixed to the ground and we start giving the top plate a velocity, okay. So, when the top plate starts moving with a velocity v in the x direction. So, it tries to pull all the fluid element or the molecules that is in contact with the plate, it also try to move it along the plate. However, the bottom plate is fixed. So, all the fluid element or fluid particle that is in contact with the bottom plate will try to restrict that flow. Okay. So, they try to have in the same resting position. So, because of that this kind of a profile will generate, the linear profile will generate. Okay. So, if we want to measure the shear, in this case the shear rate, that we can measure by how long the top plate has moved on from a particular point and what is the distance between these two plates. Okay. So, if we consider the continuous shearing at a constant rate, that means this top plate is moving with a fixed velocity v towards x direction, then shear rate, that is also called the strain rate, is defined as gamma dot. Okay. So, gamma dot is the shear rate or strain rate or rate of strain, any way you can express it. That means the change of shear with respect to time. So, d gamma by dt. So, it is a time dependent material function. So, now d gamma, gamma is the shear. So, we can express this as small distance if it has changed. So, dl by h. Okay. Now, dl by dt, that's it is significance of the velocity. So, velocity divided by h. So, if you want to measure here the strain rate, we can express it in terms of the v and h, and here the delta L and h is very small that we have considered, right. So, now fluid behavior in steady shear flow. So, to completely describe the state of stress or strain, 3 directional flow should be considered. For steady simple shear flow in the Cartesian coordinate, the stress tensor is used to express the flow, as I have mentioned already in the last class. Now, viscometric flow or simple shear flow. So, what is that? That linear relationship between the shear stress and the rate of shear strain governed by the viscosity of the liquid. Now, what is viscosity? As we have seen in the earlier diagram, that if unidirectional shear stress is applied, that is towards the x direction, the plate has been moved with a velocity, constant velocity v, then because of the fluid property, it try to resist the flow. Okay. So, that is termed as viscosity, and if we plot the linear relation between the shear stress and shear rate, we will get a straight line, and the proportionality constant is mu or viscosity. Okay. So, here is the expression, graphical expression, that is shear rate we have expressed in x direction, and the corresponding shear stress which is expressed by tau, that is being given in the y direction. So, a straight line we are getting, and from the slope we can get the idea of viscosity. Okay. Now, those material which show this linear behavior between the shear rate and shear stress is called the Newtonian material, because they obey the Newton's law of viscosity. So, this tau is equal to mu into gamma dot, that is the Newton's law of viscosity, and the fluid those will obey this law is called the Newtonian fluid. So, in case of Newtonian fluid, if we want to plot their viscosity at different shear rate, so we will get a straight line, because from this plot also we can see that the slope does not change, it is a straight line. So, the slope is actually the idea of viscosity, the concept of viscosity. So, any point, any increasing shear rate, if you want to measure, you will get the same slope. So, apparent viscosity does not change, viscosity or apparent viscosity does not change. Normally, we in case of Newtonian fluid, the viscosity is represented by mu, and in case of non-Newtonian, we generally express them by apparent viscosity eta. Okay. And also this the slope that we are getting, this is termed as dynamic viscosity. Okay. So, dynamic viscosity here remain constant for all shear rate. So, dynamic viscosity mu, that is equal to at any instant if you want to measure, that is d tau by d gamma dot. Now, here are certain common liquid that is food only, or the application of different food is related with this kind of liquids. So, in them we can see that for water, this value of dynamic viscosity is 1.002. Okay. The unit is in Pascal second. Ethanol we are getting 1.20, milk we are getting 2, olive oil we are getting 84. So, you can see that viscosity is changing or increasing, okay, in this particular material. So, viscosity is therefore a property that resists the flow of the fluids, and like we have learned about the dynamic viscosity, we can also express the kinematic viscosity in terms of mu by rho. Okay. So, dynamic viscosity, as I said, that Pascal second is the unit in the SI scale, poise in the CGS system, and nu, that is the kinematic viscosity expressed in meter square per second. This is actually the similar to the heat transfer alpha, that is called the thermal diffusivity, and also the mass diffusivity. Okay. So, this is similar in case of the momentum transfer. If you consider, you will express this particular parameter by the kinematic viscosity. Rho is the density of the fluid in kg per meter cube, and phi, which is the reverse of viscosity, this is called the fluidity or flowability. Okay. So, flowability is just like 1 by mu. Now, viscosity of the fluid is a consequence of the molecular interaction within the molecular structure of the material. So, this is very important, because what happened that why we feel the viscosity, or viscosity will change from material to material, because there is molecular interaction playing a role, and not the molecular interaction among all the material is not of similar type. There are different kind of interactive forces acting in them, and molecular thermodynamics reveals that the temperature has a direct effect on the molecular motion. Okay. So, there is a some kind of trade off happen between the thermal energy and the molecular energy, okay, intermolecular energy. So, viscosity therefore must also depend on temperature, because sometime when we apply heat to the material, what happened to the viscosity? For the liquid, if you have observed that the viscosity lowers, right, and in case of the gas, viscosity increases. Okay. So, the interparticular particle attraction or interaction force reduce because of the thermal energy, and then the viscosity lowers. So, the interaction plays an important role. So, viscosity will decrease with increasing temperature if no other reaction or transformation are involved. Okay. Sometime say for example, starch gelatinization. So, if we provide heat to the starch in the moist condition, so gelatinize happen, and that will change the structure of the material, okay, and gel formation will be there, and the viscosity increases. So, the nature of the temperature dependency of viscosity can be expressed as Arrhenius kind of equation. So, mu, that is equal to a constant A into e to the power b by t, or it can be also written as A into e to the power E A by R T. So, B is equal to E A by R, and E A is the activation energy, R is the universal gas constant. That means, if it follows this kind of an equation, and one temperature at a particular temperature, if we know the viscosity, then we can express the viscosity at any other temperature following this behavior, right. So, this is the representation that ln of mu by mu r, that is equal to E A by R into 1 by T A 1 by T minus 1 by T R, because for a particular fluid if you are considering, so activation energy will be same, R will also be same, but T is different, temperature will be different, and because of that the viscosity will be different. So, for any fluid we can apply this equation to see the temperature dependency of viscosity. Okay, so, this is the normal expression, the units of all these parameters. So, as I said that bonding energy and thermal energy, these two will play a role in increasing or decreasing the viscosity. Okay. So, Next is viscous fluid. So, viscous fluid tend to deform continuously under the effect of an applied stress. They can be categorized as Newtonian or non-Newtonian fluid. So, by now what we have learned is that if we apply a steady shear on a material that will flow instantly, those are fluid material, but if we plot the nature of the shear stress and shear rate, okay, in y and x direction respectively. So, what is the nature of that plot? Okay. So, if that nature is linear, then those fluid will be considered as the Newtonian fluid, and if they are not linear, then we can term as the non-Newtonian fluid. Okay. So, obviously Newton's law of fluids, Newtonian fluids, they will follow the Newton's law of viscosity, and viscosity is constant and independent of shear rate. For example, gases, oils, water, and most liquid that contain more than 90% water, such as tea, coffee, beer, carbonated beverage, fruit juices and milk. Okay. So, these show Newtonian behavior, right. So, definitely you need to take a fluid element. Now, if you consider a whole vegetable or fruit, although sometimes they consider they have higher than 90% water, but they cannot be considered here. You have to look for the fluids. Okay. Now, non-Newtonian fluid. So, here is the plot that shear rate and shear stress we have plotted in x and y direction respectively. So, the straight line where the slope is constant, that comes under Newtonian, you know that already. Now, these two plot where we are getting one curve that is changing its slope at every instant of changing in the shear rate, and as shear rate increases, okay, as shear rate increases, we are getting a decreased slope, right. Similarly, the other the lower curve, if we can see, where with change in shear rate we are getting an increased slope, right. The other particular nature here we can observe, that is a straight line, but that straight line does not pass through origin. Okay. So, all such characteristics that is deviating from the ideal Newtonian behavior, where the stress and strain shear rate relation will be straight line and that will pass through the origin, is not being fulfilled. So, these all are comes under the non-Newtonian fluid. Okay. So, they do not follow the Newton's law of viscosity, shear thinning and shear thickening fluid, and they obey the power law model. This is also called the Ostwald-de equation, that is tau y x is equal to k into dvx by dy to the power n. So, see tau y x, that means if we consider the flow is in x direction, we are considering the flow is in x direction. So, V x. Okay. So, the stress shear stress felt in y direction because of flow in the x direction. So, that it indicates, as I mentioned in my last class as well. So, this is the shear stress tau y x, that is equal to k into dv x, that is change in the velocity dv x in the dy. Okay. Okay. So, this is it. Now, we can see here we have a power n as well, that is why it is called the power law model. So, k is the consistency index and n is termed as the flow behavior index. So, the unit of k is in Pascal into second to the power n, and n is the flow behavior index. For shear thinning fluids, as I said that the slope is decreasing, that means viscosity is decreasing with every increase in the shear rate. So, then n is less than 1 and the other case where the shear thickening happen n is greater than 1. So, non-Newtonian flow behavior, that is viscosity is not the same at different shear rate, non-linear relationship between shear stress and shear rate gamma, or the flow behavior curve does not pass through the origin, that is another case which happen in case of a Bingham plastic fluid. Okay. So, non-Newtonian fluid, that is why we call the apparent viscosity eta, and for the purely Newtonian viscosity, Newtonian fluid, we use the viscosity mu. Now, the ratio of shear stress to the corresponding shear rate is therefore called apparent viscosity. The ratio of shear stress, shear stress to the corresponding shear rate is therefore called the apparent viscosity at that shear rate, because as shear rate changing, this value is also changed. So, eta, which is the apparent viscosity, that is a function of shear rate here, because at a fixed shear rate we are getting this apparent viscosity, it will vary at different shear rate. So, eta at a fixed shear rate gamma dot, because it is a function of gamma dot, that is equal to tau by gamma dot, because ultimately what is apparent viscosity? If we plot the shear stress versus shear rate, then we get the slope of that is called the apparent viscosity. So, this apparent viscosity is which is viscosity in case of Newtonian, that is fixed, that does not change with the shear rate, but here it is changing with the shear rate in case of non-Newtonian fluid. So, what we can write is, we can write eta of gamma dot, tau is here k, that is the consistency index, into gamma dot to the power n, because it follows the power law equation, by gamma dot. So, we can write k into gamma dot to the power n minus 1. So, this whole term is referred as apparent viscosity, consistency index into shear rate to the power n minus 1. So, intrinsic viscosity, what is it? Intrinsic viscosity can be determined from dilute solution viscosity data as the 0 concentration limit of specific viscosity eta Sp divided by the concentration C. So, eta and eta S are viscosity of the solution and the solvent respectively. So, eta is limit concentration tends to 0, eta Sp by C, and eta Sp equal to eta, that is the viscosity of the solution, minus eta S, that is viscosity of the solvent, divided by eta S. So, as I mentioned that shear thinning behavior, where we can observe that the apparent viscosity is decreasing with increasing shear rate. So, this is shown by this trend. So, apparent viscosity, here we are plotting eta, that is equal to k into gamma dot to the power n minus 1. So, shear thinning is this behavior, and the flow behavior curve has a convex profile in which the tangential slope is decreasing, that we have seen in our stress versus strain shear rate plot. If you remember the tau with respect to gamma dot, we have got this kind of a plot for shear thinning, and the reverse we have got for the shear thickening. So, shearing causes what kind of changes in a food? So, it causes entangled long chain molecules to straighten, and because of their straighten out, they become aligned with the flow, reduces friction between the two layers and also reducing the viscosity. So, because of this kind of nature, some food or some material show this kind of behavior, where upon higher shear or increasing shear rate, their viscosity reduces. So, example of this pseudoplastic food, that is shear thinning food, are fruit and vegetable products such as apple sauce, banana puree and concentrated fruit juice, cake batter, etc. So, for all this, if you put higher shear rate, we can get the viscosity as will be reduced. Now, rheological behavior of the food may change depending on concentration. Okay. So, because they are not, that is why the concept of the intrinsic viscosity is important, because when the concentration is high, then the viscosity will change, and sometime it also happen that because of higher concentration sometime agglomeration may also happen. So, the bonding it shares between the fluid and the particle will be changed, and the particle interaction will increase, right. So, this happened in case of a concentrated grape juice, where 82.1 degree Brix showed shear thinning behavior. However, diluted sample, that is 52.1 to 72.9 degree Brix, were found to be Newtonian. So, what happened is that, when see 52.1 to 72.9. So, this much degree Brix concentration when we have considered. So, we are getting a Newtonian trend. Okay, that means, as shear stress is increasing, shear rate is also increasing, shear stress is increasing, right. Now, what happened that when we reaches a higher concentration, then maybe the grape juice, in that the particle that were immersed. So, they will be coagulated or they will be agglomerated. Okay. So, because of that, what happened that their interaction with the fluid particle will be lowered. Okay. So, shear thinning behavior we can observe. So, because of that agglomeration, the behavior of the liquid will be totally changing. The reverse trend, that is shear thickening, which is the behavior where shear stress and viscosity increasing at an increasing rate with increasing shear rate. So, normally this is seen in high concentrated suspension. For example, cornstarch suspension, waxy starch, that is maize, rice, barley and potato, and this also called the dilatant behavior, that is with increasing shear rate the liquid between the solid particle is squeezed out, and in turn more friction will be generated, right. So, this increasing friction account for increasing shear stress and increasing the viscosity experienced as shear rate, that is also increasing. But because of squeezing, it causes dilation, that is increase in volume, okay, of the suspension, and therefore, this phenomena is called the dilatant flow behavior. Now, you often may get to get to accommodate with this term like true dilatancy and apparent dilatancy. Okay. So, true dilatancy means that when you apply the increasing shear rate, your behavior changes, that means your shear thickening happens, but when you withdraw the stresses or the shear rate is again come to 0, you can get back the initial viscosity. So, those materials show the true dilatancy, but certain material, because of their structural permanent changes, okay, permanent structural changes may happen in them. So, when the shear rate is again reduced to 0 also, their viscosity does not come to initial condition, right. So, those are called the apparent dilatancy. So, simply if you can compare the apparent viscosity with increasing shear rate for Newtonian, for lower and higher shear you will get the same apparent viscosity, whereas the non-Newtonian fluid you can't be sure of, they may go very low with higher shear rate, or even go little bit lower compared to the Newtonian or compared to their initial value when the shear rate is increasing. Okay. So, this is the different kind of nature we can observe. So, therefore, the viscosity will depend on the stress condition, that is shear rate, and often on also time in case of the non-Newtonian fluid. So, we will stop here, I will continue in the next class. Thank you.